Okay, so while that is going on, I want to welcome you to my lecture today. And of course, I gonna make this announcement based on what what I've seen so far in terms of grading. I think everyone in this class has done excellently well, and I hope at the end of the semester, what is going to be my joy is if I'm able to maintain that and everybody has A in this class. I'm actually going to throw a party for that. So in case you get stuck, please make sure you ask a question. Today we're going to continue with Gaussian mixture model, and of course the assignment for this week centered on Gaussian mixture model and the density-based clustering approach that we did the other time. I will advise that you listen and ask questions where necessary. Today, of course, on Friday, I introduced you to Gaussian mixture model. What I said, we're going to continue from where we stopped today, Monday, and with the main focus on expectation maximization algorithm. The expectation maximization algorithm is actually it's an algorithm used uh, when you are doing clustering that has to do or where you apply the Gaussian mixture model. In the outline, I'm going to walk you through, we're going to have review on Gaussian mixture model. Then I'm going to introduce you to expectation maximization algorithm that we use and how do we do this in R. How do we get here? We remember, you remember the other time when I introduced a density base, the density based clustering had some of its advantages and also has some disadvantages. And it's because of the disadvantages that we observe with the density base, and that is the reason why we want to consider a Gaussian mixture model. Now, you remember the advantages that we have with the density base is the ability of that to be able to handle any arbitrary shape, okay? Particularly if you're talking about crime spot, detecting crime spot, okay? So it will enable us to identify clusters of hotspot locations that may be irregular. Of course, we all know that. Then it also, the density-based algorithm also enable us to identify noise and outliers. At times we could, we could have some hotspots that actually maybe isolated, location with isolated crime events. So of course, the density-based algorithm will enable us to identify all of that. And of course, with density-based, we do not need to predefine the numbers of clusters ahead of time. That can be determined from the data. And of course, the density-based efficient with the large data set. But the reason why we actually move from the density-based algorithm to the Gaussian mixture model is because of its sensitivity to the parameters. So what are the parameters that we talk about? We talk about the minimum distance parameter. You talk about the minimum number of points to be classified as, okay? The other small one, that's a pi, that is the missing coefficient that we talk about, okay? And if you take a look at this now, if I know the values of a latent variable z, what is the probability that a particular data point actually come from a particular cluster? That's going to be a conditional probability. So if you take a look at what we have here, it's actually trying to tell you that the pi k that I talk about here, okay, the pi k that I talk about here, this particular pi k, is actually a Gaussian distribution itself. It's a Gaussian distribution itself. Okay, you can see, what did I substitute? I'm substituting pi k. You know, whenever you see something that way, that's a Gaussian distribution. I'll tell you, you got a variable Sn, okay, where for each cluster, um, the mean vector exists, and the variance covariance also exists. Okay, so that is actually going to be used for that. And of course, I made some derivation. If I have this to be using the knowledge of conditional probability, if I have that, I can find the probability of xn, which is going to be all of that. And if I continue to go, okay, I'm going to have the probability of s to be that. And finally, you know, using the fact that the probability of a zk equal to 1 equal to pi k, and the probability, the conditional probability, if I observe a latent variable to be equal to 1, the probability of xn, okay, actually going to belong to a particular cluster. What I'm trying to say is that follow normal distribution, follow multivariate Gaussian distribution, as you can see. And using the idea of a Bayes theorem, we're actually going to come out. Why are we using the idea of a Bayes theorem? If you take a look at what I have here, the probability of zk equal to 1 given Sn is going to be equal to the probability of xn given zk equal to 1 multiplied by probability of xn. Now, when you take a look at equation 4, that's a posterior density. Posterior. The idea, has anybody heard about Bayesian statistics? Okay, thank you so much. In Bayesian statistics, we actually use the knowledge of posterior density. You know, the idea is to update our prior belief. Okay, you know, with the likelihood, we actually going to get posterior. When you take a look at what I have in equation 4 now, that is a posterior density. We use posterior density. We normally maximize the posterior density in use, you know, when we are working with the Gaussian mixture model. Now, let me tell you this. The approach that we use, okay, in the Gaussian mixture model is what we call expectation maximization algorithm. Okay, we're going to first start with the expectation. We want to be able to know the expected number of cluster assignment, and after that we update. Okay, that will follow by maximization. And let me tell you this, we got 3 parameters that we normally want to maximize: the pi, which is the missing coefficient, the mu vector, and the variance covariance. That's all we want to figure out. Okay, now step 1. Now let me tell you this. If you want to run your algorithm, you need a very good initial starting point. So how fast? And if you want to talk about the convergence rate of algorithm, of course, it depends on the starting point. We actually want to get the maximum values. We want to get the parameter, pi, mu, and variance covariance, and we need to initialize theta. And the good way to start is to use k-means. You remember we've done k-means in this class, k-means algorithm. Also, if I want to have a sense of what initial starting point that will work for my parameters, we don't just choose them arbitrarily. We're actually going to start using a k-means, which I'm going to walk you through it now. Take a look at equation 5 now. Okay, I'm not talking about the expectation step. I told you expectation maximization. Before first start with the expectation, what am I trying to do here? And that's why, take a look at that. Oh my God, it's like the lean. I told you the other time why we have to take the logarithm. Okay, when you have a likelihood function, if you don't forget the likelihood function is a product of the density function. I want to maximize something that is multiplicative in nature. That would be computationally intensive, and that is why we bring in the log, okay, the natural log. The natural log is to simplify because the natural log is going to make something multiplicative to be additive, and that will be super cool to work with. Now, I'm taking the expectation of that. Take a look at that. Taking the expectation of that, if you take a look at this guy now, it means that a random variable here is, let me show you what random variable here is. Please pay attention. This guy is a random variable. The whole of that lane of that is a random variable. And I want to find expected value of S in a traditional statistics. When S is a discrete random variable, expected value of S is going to be summation X multiplied by probability of S. Do you remember that? That is exactly what we're using here. Take a look at that. That was why you have summation dot. Okay? Now, the moment we have that, you can actually incorporate, well, what is the probability? What is this guy? And what is that guy? Based on what we've done before, you can plug that in. Okay, the moment you plug them in, that will take you to equation 7, okay, and finally to 8. Now, this is the final equation, okay? But there's something that is missing in this equation. What is missing in this equation is that we did not impose condition on missing coefficient, because the sum of the missing coefficient must be equal to 1. Because of that, the optimization we want to do now will be a constraint optimization, and that is what is going to take us this today. Look at equation 8. What have I done? I'm adding a Lagrangian multiplier. Take a look at that, believing that, trying to impose a condition that summation of pi must be equal to 1. If you don't do that, there's possibility you're actually going to go out of bound for pi. Pi is very important, the missing coefficient. Does that make sense? This is what the equation 8 is the final model that we're actually going to optimize. Now, how many parameters do we have in this model? We got pi, which is the missing coefficient. We got mu, which is the mean vector. And we also have the variance, covariance. All what we're just going to do is to differentiate, to conduct our partial derivative one at a time. Take a look at that. We're going to differentiate that with respect to pi k. I'm going to set to 0. I'm also going to do the same with respect to mu. I'm also going to do the same with respect to variance, covariance, set to 0. And at the end of the day, oh my God, take a look at this. That's what I'm going to get for the pi k, which means pi k can be determined. Okay, that's a missing coefficient. Then what am I going to get? So for the mu k, when you do the same, I'm going to get this guy for the mu k. I'm going to get this guy for the variance, covariance for a particular cluster. Where do I get the 3 equations from? I got that by optimization. What I did, go back to equation 8. I differentiated equation 8 with respect to pi, with respect to mu, with respect to variance, covariance, and when I differentiated with respect to pi, other parameters will be regarded as a constant. And that's what make it to be a partial derivative. When I differentiated with respect to mu, okay, pi and variance, covariance will be regarded as constant. When I do the same for the 3 of that, I equate to 0. I solve for that. I'm actually going to have this right now. Okay. Now, that is a theoretical development of that. Why am I showing you this theoretical development? Because it is only when you understand the theoretical development of how we derive the parameter that you'll be able to modify, because things are changing in real life. We can have a way to remodify the equation. Okay, maybe break something in, because of the fact that situation is dynamic in nature. And that is the reason why you need to understand the way they handle the conventional. And that's why we're showing you now. Now, you know what we want to do now? I want to take us into R. I want to take us into R. Gaussian mixture model in R. You got a lot to do in the lab this week. My TA is going to walk you through a lot of stuff. Now, take a look at this. How do we do Gaussian mixture model in R? You need to load an essential package, mclause. Okay, mclause, you're going to load it, the package. And you know what I want to do? I want to start with the with fabricated data set. So here I'm simulating. And whenever you simulate, like when I give you assignment, I normally say set a seed and to be the same number, so as to have the same set of values to work with. You know what I've done right now? I'm actually simulating 3 sets of data. Each of them follow normal distribution. I needed to take a look at that. They got the same standard deviation, but different of means. The mean 0, 5, 10. And 100 we mean for 2 column. 100 for 2 column will mean 50, 50. Does that make sense? Okay. Now I want to perform our GMM clustering. You know why we perform, the GMM clustering is a soft clustering where we believe a particular object can be in more than one cluster at a time. And in situation where that occur, we're actually going to apply probability approach. That's why we call that probabilistic assignment. Okay. Now here, we already have my data set. Okay. So the M cluster of data K equal to 3, the number of clusters. Let me tell you, if you want to work with with this with Gaussian mixture model, okay, we specify the number of clusters ahead of time. Okay, now I told you in the expectation maximization, we start with the expectation of what the number of cluster assignment is going to be, and that's why you see this cluster assignment. Take a look at that. You know what this guy is trying to tell you now? Okay, some are in cluster 1, some are in cluster 2, and some are in cluster 3. That's what I'm telling you now. And they're going to be 150, don't forget. 100 into 2, 50, 50, so it's 150. Okay, take a look at that. Then a code to visualize, if you want to visualize result, the assignment, and you actually want to generate. So this is the way to visualize that. I needed to take notes of that, and you can see a particular point here, both black and red. Look at that. So that may be able to go into the black group and also go into the red group. Of course, our probability assignments required. I'm going to go into another set of data. This time around, what I want to do, I want to simulate the combination of a normal and the anomalous, and anomalous data. I say anomalous data, maybe the one with outliers. I want to do that now. Take a look at the code right now. I want to simulate, it's like simulated to a set of data. Okay, one, you can see arrow num 1000. Don't forget 2 column. That will be 500, 500, right? And the anomalous data 50 for 2 column, 25, 25. What is the totality? That will be 525, right? 525. Now, we want to fit a Gaussian mixture model to the data. Okay. Now, assuming there are 2 components, because we already know, we got the normal, we got the anomalous. By the time you specify that, it's going to give you this. It's going to tell you 500 points in out of the 525 is in cluster 1 and 25 in cluster 2. Now, let me tell you, I got a presentation to make tomorrow, but Nigerian time, because that's a Nigerian university. I would have advised that you join, but you can't. There's no way you're going to join because it's going to be 3:50 a.m. American time. So, and the presentation I want to make it has to do with using the Gaussian mixture model. Okay, I incorporate that into GAC model in time series analysis. They make use of star model, star GAC model, a transition regime that is static in nature, and decided to incorporate the Gaussian mixture that is soft in a way. So, and the bottom line is, if I want to know the impact of Inflation Reduction Act, passed into law in August 16, 2022 in the United States, if I really want to confirm the position of government on that, because I know inflation is connected to so many sectors, okay, energy price, medical costs, and so on like that. The model we're going to use, there's going to be a lot of non-linearity. So I'm bringing in the Gaussian mixture model to partition the inflation period into different kind of regime, as against the one they use in conventional statistical literature of a smooth transition gag. Okay, I'm speaking too much. So I have that presentation. So what I'm trying to say is that with Gaussian mixture model, if you have some set of data that have different switching regime, of course, this can partition into different, clusters for you, and such a way that some points in this cluster can also be in another cluster, and that's why we can have the probability. Now, we normally make use of BIC. There's a lot of models that came out when we did this, but we picked the best. The model with the smallest BIC is the best. So in this partition now, okay, cluster 1 got 525 different data points, and these have been classified into 2. Okay, I need to take a look at that. So the BIC, the log likelihood, actually measures the fit. Where your BIC is very low, okay, the smallest BIC indicates the best model. Okay, now I want to go into another set of data. Okay, with this data set now, let's say for instance, I have data set like this. I want to use a Gaussian mixture model. How are we going to do it? The very first thing you're going to do, don't forget to run the Gaussian mixture model. You actually need very good initial point, right? Initial starting point, right? And what did I say? We need k-means. First, you do k-means, right? Okay, before you do k-means, don't forget, load your package, set the seed. Now, take a look at this. What do I want to do first? To run k-means. Okay, why am I running k-means? Running k-means because I actually want to use the values generated by k-means as the initial starting point for my algorithm in the GMM. Okay, now extract k-means centroid. What we need is the centroid. The centroid in k-means is just the center of the cluster, the mean of the center. Okay, now what is this? What am I saying? Extract the k-means centroid, the initial means. Okay, and after that, we can get the cluster assignment. You can see the cluster assignment of that based on k-means. Okay, and after that, after doing that, please listen. The first major step in GMM is to run k-mean clustering. That is the first major step. The algorithm is called expectation maximization. The expectation angle. I need initial point. A very good initial point. I can get that using the k-means. That's why the step 1 is run k-mean clustering. And after that, step 2, initialize GMM parameters. How are you going to initialize the GMA parameters? If I say you initialize that, you need to initialize the mean, initialize the covariance. Look at that. Now, if I want to initialize the mean, I'm actually going to use the value that I got from k-means. Then how do I initialize covariance? This is the code to initialize covariance. Put your data in, okay, with this together with this, okay. And alternatively, you can run this code to initialize covariances. Oh, I've initialized means I've initialized covariance. Oh my God, there's something more to initialize. Don't forget we got 3 parameters with GMN. Also need to initialize weights. Look at that. That's a code. Initializing weight is so easy. What is that? The table, cluster aside divided by n row data. That's going to be the weight. And after we're done with that, okay, we're ready to load our package. Okay, load the package. Then create the GMM model with initialized parameters. Okay, then fit the model. And after fit the model, then you get a summary of that. Okay, now that is step 3. Okay, now the next thing is to see results. That is it. That is the result. What has happened now? The 150 data set has been partitioned into 3. Cluster 150, cluster 250, cluster 350, because we got a lot of modules, a lot of results, and Arrow automatically choose this one based on is the one that have the smallest value of BIC. Is there any question at this time? Go ahead. The lowest. Yeah, the lowest. The lowest BIC is the best. Yeah. Okay, now another example right now. Oh my God. I want to go into the real life example now. I've been using simulated data set. Now, dietary survey, IBS. Okay, if you want to have data, if you want to have access to this data set, you need to load a package called cluster R. And if you write data dietary, so of course you're going to have access to your data. When I look at the dimension of the data set, it's 400 by 43. That's a lot. 400 number of observation, 43 features. Does that make sense? Now, if you take a look at this, there's response variable in that data set. We don't need it because we want to act blindly. I say there's no label. Don't forget, we're talking about unsupervised learning, right? And the only way to know whether a particular algorithm is going to work in clustering, do you know we can use that we can use data set that already have label and remove the label, use your model, use your algorithm, and compare what you get with the label. That is the way to know whether your algorithm is doing a great job. Okay, so you scale the data and we perform the GNN on that. Okay, and we make a prediction. Take a look at that. Do you know what I'm trying to show you now? If you want to have a kind of see so many BIC, you know, the other time I said the one is the smallest BIC. This is like showing for across, there's going to be a BIC generated for a particular number of cluster, just like that is similar to what you normally see when you work with other algorithm where we make use of EBO and GAP. Okay, here we're making use of BIC. Okay, the cluster with the smallest BIC is actually going to be the best cluster. So what is it talking about? It's pointing at cluster 2. Saying 2 clusters because that's the smallest BIC. Okay, lastly, another real data application. This data set provides 13 measurements obtained from chemical analysis of 178 wines grown in the same region in Italy, but derived from different cultivars. Let me tell you this. We want to see whether they have or whether the Gaussian mixture will be able to classify data point into, into the appropriate cultivars. The natural grouping already exists here. Barolo, Granonilo, and Barbera. I need to pay attention now. We're working on real data set, real life data set. And the same, in the assignment, they're going assignment. I think, what was the data? Iris data, if you check. Okay. Now, the data, if you load that package G cross, you're going to have access to wine data. Okay. Now you see the class label, but you know what? We want to blind the process. We want to remove. What do you think I'm doing here? -1. I'm not interested in the label. We want to use our algorithm to do the partition. Does that make sense? To make it an unsupervised. Okay. Now I'm going to do analysis. Just X, that they're going to be the minus data dot matrix wine -1 removing. It means I want to remove the labels. I want to do the partitioning using the Gaussian mixture model and be able to compare with reality. Okay. Now I do MOD, I do the summary of that. I'm using the criteria, the BIC. Oh my God, this is what I have. You know what he's trying to tell me now? Do you know my Gaussian mixture model correctly predicted the number of clusters? We knew that from day one that there were 3 clusters, right? The Barolo, the Bregolilo, and the Barbera. We knew from day one, but we removed that from the data set. We want to see the performance of the Gaussian mixture model, and that successfully identify 3 clusters. It's like, oh, 63 of that is in 1, 51 of that is in 2, 64 of that is in that. But you know what we're going to do next? We want to see whether he was able to identify the number correctly. You know, he has done a great job identify the 3 clusters that we have. Another question, does he really identify the number correctly within each cluster? And that is why we're going to go into analysis of misclassification. Take a look at that. Table, class. If you want to know, then you now make use of the label that you remove initially. You now want to compare. Oh my God, that is part of the assignment that I just gave yesterday. Now, this is going to enable us to know the probability of misclassification. Let me tell you this. Even though we want to use a model to depict reality, a model can never give us an exact characterization of reality. There's always going to be a gap. I don't expect a Gaussian mixture model to actually have 100% classification rates. I don't expect that. But I want a situation where the classification, the correct classification will be maximized. And if you take a look at what we actually have right now, if you take a look at in class 1, okay, you know, it's X61, and this is going to give us opportunity to be able to know how many of this, how many of that, and so on, like that. But let me tell you this. If I really want to tell, I need adjusted round index. The adjusted round index value needs to be so high, okay? And in this case, it's very high. So which means he has done a great job. Now, I needed to take a look at this. This is class 1, 2, 3 against the conventional, the clustering style. I needed to pay attention to that. But because of the high value that we have, then that really indicates that the method has done a very great job, even though it hasn't done that perfectly, which is typical of any statistical or machine learning algorithm. We are done with clustering today. Okay, we are done with clustering. And you know what I'm going to do? Latest Thursday, I'm actually going to post exam 1 practice question for you to be able to see. And I'm also going to dedicate a time, a class where I'm going to revise what we've done before and how I expect you to tackle problem uh, with exam one. Okay? So is there any question before we go, before I go today? Any question? So like I said, up to this moment, you guys are doing great. But let me tell you this. I may not know whether you are doing great statistically until when we do exam one. Does that make sense? And if there's anyone who still gets stuck, please reach out to me. Make sure you all stay safe and have a lovely day. Bye for now, everyone.